Alrighty, welcome back to part 2 of our discussion of biopsychology. So we were talking about epigenetic effects and situations where your environment kind of interferes with the way that your genes are going to be expressed. We just talked about the reaction range, and now we're going to talk about another important theory that's very important in the study of psychology, especially if you go into abnormal psychology and psychopathology, which is called the diathesis stress model. If you take abnormal psychology with me, I will absolutely hammer this into your brain. This is a very important model in psychology to understand. So the diathesis stress model is used primarily in explaining psychological disorders. The idea behind it is that your genetic and your biological predispositions are interacting specifically with your stress responses. And if the combination of your genetic predispositions for a certain disorder and your life stresses, if those two combine to exceed a certain threshold, this disorder is going to manifest. We use the diathesis stress model in talking about anxiety disorders. We use it in talking about depressive disorders. And one really easy to see example where we use it is in talking about schizophrenia. So there was a study that was done. This is a perfect example of the diathesis stress model. There was a study that was done, and they looked at children who were adopted, but we were able to trace back and know for certainty that that child's biological mother had been diagnosed with schizophrenia. Now, backing up just a little bit, we know there is a genetic component to schizophrenia. Like it's not debated, it's not up for question. We know it is there. There is a genetic link for schizophrenia. It exists. So what they were trying to determine is if these children have been adopted, right? So they're removed from that situation and they're not actively being raised by someone with schizophrenia. Are they still more likely to develop schizophrenia later in life? And does that depend on whether they grew up in a disturbed family environment or in a non-disturbed family environment? Because, and the reason this is important, side note, if you're interested in the study of disorders, there's a lot of concern that when we talk about the genetic influence of disorders and we're studying kids who are being raised by the biological parent with that disorder, is it actually a genetic transmission of that disorder, or is it that the kid grows up seeing their parent act that way and it's more of like an emulation or a social learning phenomenon versus an actual genetic transmission? So that's why adoption studies are so valuable, is it gets rid of that concern. It controls for that variable, as we learned when we talked about research methodology. So adopted children, biological mom who had been diagnosed with schizophrenia, DX is psychology shorthand for diagnosed, and biological mom with no diagnosis of schizophrenia. And then looking at a non-disturbed family environment or a disturbed family environment. So what they found was fascinating. So in all three of these groups, the biological mom who had schizophrenia, but the kid was raised in a non-disturbed family environment, and the biological mom without schizophrenia. For all three of these groups, the likelihood that that child would end up later being diagnosed with schizophrenia was all about the same, and it was all very low. There was like a 4.8 to a 5.8%. So what that found is, yes, these children may be carrying the genes for schizophrenia from their mother, but growing up in a non-disturbed family environment seemed to protect against those genes ever being expressed, right? Because if we come back up here, they did not have that life stressor that pushed them over that threshold for the schizophrenia to manifest. But down here, where you had kids who their biological mom had a diagnosis of schizophrenia and they were raised in a disturbed family environment, their likelihood of later developing schizophrenia was 36.8%. So you can see this is way, way higher. But it's because we added in that variable of the increased stress. And that's the whole element of the diathesis stress model. When I teach abnormal psychology, the example that I give is like of a light switch, right? That if you have a genetic predisposition for a disorder, it's like you're born with a light switch. And this amount of stress that happens in your environment, the amount of trauma in your environment, is what's going to determine whether or not that light switch is ever flicked on. Another person could go through those exact same stressors and not develop anxiety, not develop depression, not develop schizophrenia, because they weren't born with that light switch. That genetic predisposition is not there. So that's an easy to remember kind of symbolism for the diathesis stress model. So epigenetic effects is where your genetics and your environment combine. It's that thing where when somebody says nature versus nurture, well, the answer is always both, right? They're always working together. Once you get outside talking about your height and your eye color and whether your second or your fourth finger is longer or how your hands interact, right? Like there's most of the things when we're talking about behavior and personality, you're going to be talking about epigenetic effects. So now we're going to transition a little bit and we're going to talk about the brain and the mind. How do the brain structures, the brain chemicals, actually translate to that more conscious element of our mind and how we experience our emotions and how we experience our realities? Again, I'm not reviewing every single brain structure, but a few things that are interesting, that provide interesting discussions. First of all, the limbic system. Absolutely remember the term limbic system. The limbic system is the part of your brain that's made up of several different structures that plays the primary role in your emotions and your memories. The limbic system categorizes your emotional experiences as being either pleasant or unpleasant. Part of how it does this is one of the structures in the limbic system is the amygdala. The key word to keep in mind with amygdala is fear. Your amygdala is a key player in producing fear and in forming fear-based memories. If you get startled and you start to have that fight or flight type of reaction, right? That's your amygdala kicking in and going, oh, do I have something I need to be scared of here? Okay. Close to the amygdala, also in the limbic system, is the hippocampus. Now, the hippocampus does a bunch of different things. I don't want to oversimplify this. But one thing that the hippocampus does in conjunction with the amygdala is when that amygdala kicks on and says, oh, be scared. The hippocampus is supposed to be kind of in the background logically evaluating and saying, is this perceived threat something that I actually need to be afraid of? Okay. If you're walking through the zoo and you hear a lion roar behind you and you jump up and you turn around and you realize you've just walked with your back to the lion cages and didn't realize it, your amygdala is going to kick in. Lion, fear. But your hippocampus is going to immediately follow up. Nope, he's in a cage. I'm at the zoo. We're fine. Totally different reaction than if for some reason you were out on the plains of Kenya and suddenly you hear a lion roaring behind you, right? And you're in a wildlife preserve or something. You hear a lion roar, you turn around, and yeah, your hippocampus is going to say, yep, real threat. We should probably do something here. There's a lion behind you. So it's evaluating what's happening there. So one thing that is fascinating is studying this interaction between the amygdala and the hippocampus in instances where there are PTSD symptoms, post-traumatic stress disorder. Because one thing that commonly happens in post-traumatic stress disorder is there will be a noise, a startle, a reminder of a trauma that happens, and it triggers that fear center in the brain. And where the hippocampus, where you would expect it to come along and say, nope, that sounds really similar to what we experienced, but we're not in any danger right now, we're fine. They've actually found in brain scans that there's a reduction in the brain matter in the hippocampus, and it's not fully doing that in the way that we would expect it to. So an example of this is with combat veterans, right? If they have PTSD, if there's a firework, if there's some other boom, if there's some other loud noise, that amygdala gets activated because it goes back to that memory of when that loud boom could have been an explosion from an attack that was close to them, could have been from an IED, could have been from something else that was a legitimate threat to their life or the life of the soldier fighting next to them. And instead of the hippocampus being able to jump in and go, nope, it's just a firework, calm down, we're good, we're fine, that reaction doesn't happen the way that it should. And so that fight or flight response kicks in. And so you have this person that consciously in their mind, they understand, I'm sitting at home and hearing the neighborhood fireworks show, I'm not in danger. But that fear system in their brain is not lining up to that and is going, nope, we should be scared, we should be worried, we need to go, we need to do something. And that's a big part of the unpleasantness that a lot of individuals with PTSD experience, is that super active amygdala without the hippocampus jumping in and giving that accurate perceived threat evaluation. This is also why, if you don't have an issue with PTSD or with anxiety, why controlled fear can feel fun. Because when you stimulate your amygdala, when your fight or flight gets stimulated, distractions go away, right? And if you think about it, that's an important brain function. Because if I'm out in the plains of Kenya at a wildlife preserve and hear a lion behind me, and I'm distracted by, I haven't planned out what I'm going to have for dinner tonight, and not focusing on, okay, how do I get away from this lion, right? I have a problem. So whenever that amygdala kicks in, it helps you be focused, and it helps distractions kind of fade into the background. So when you put yourself in a situation where you know you're going to feel afraid, but there's still enough of that control from the hippocampus to balance it out where you know it's not a real threat, you can get that mental stimulation of, I'm not distracted about these things. I'm not worried about that test tomorrow. I'm not worried about the fact that my sister's mad at me. I'm not concerned about all these things because my brain is telling me to focus here. But you still have your hippocampus jumping and going, okay, we're not really in danger. We're feeling this, but we're not really in danger, right? Like going to a haunted house or seeing a movie or a scary movie or riding a roller coaster or one of those things. So that's why for some people, controlled fear can feel really fun. There's some very interesting research on this for why some people, horror movies are more fun than others, why some people find them more interesting than others, why some people get bored with them and some people get horrified, and some people like that feeling and some people don't. There's really, really interesting research on that. If you're interested in that topic, that might be a good thing to kind of bounce around in your mind as your final project is doing something related to that. But, okay, next, the neurotransmitters. And I'm going to have to start a new unit because I'm already at 13 minutes. Here's a brief overview. Let me get myself out of the way. Here's a brief overview of the neurotransmitters and what each of them's key role is. I'm not going to give a mini speech on each of them, but there are a couple of things that I do want to highlight here from some of them. Okay. I will stop this video and we will begin our discussion of neurotransmitters in part 3.